Good morning, friends and dear students. It gives me immense pleasure to be here for my course, Engineering Thermodynamics. As of now, I have covered Module 1 and Module 2. In Module 2, I am discussing about problem solving exercise. As of now, we have done about the heat and work, first law of thermodynamics, zeroth law of thermodynamics, phase change, pressure, temperature and volume. Also we have done about the Carnot cycle, absolute temperature, efficiency, work done, heat rejected, heat absorbed. Also Clausius inequality, how this TL by TH is equal to QL by QH. We have also seen the absolute temperature, how it is defined. These all things we have done, and today I am going to discuss about the problems related to the entropy. And entropy meaning is it is a chaos in the system. Every ideal condition wants that it should be very smooth, there should not be any disturbance. But everywhere some elements are there, those elements will create some disturbances, they will create some chaos. System will not be smooth as we feel. This type of losses, this type of randomness of the system, this type of behavior where the system is not following the ideal cases, we say that this is the entropy. Entropy is in fact the change in the entropy. We have seen from the third law of thermodynamics that at zero absolute temperature, only the entropy will be zero. Remaining all the conditions, your entropy will never be zero. It means if you see in the real life, there will be always some disturbances. You cannot do anything very smoothly. If you are doing, some people will disturb you, some circumstances will make sure that you will not get what you are expecting. Suppose I want to get the marks 100 of 100. I am working hard, so much work I am doing every day. I am trying. But at the last day, I may get some small fever. So, that fever will not allow you to mentally, you will be the peace. You will be always having some stress and you will not get what you were expecting due to your physical issues. Same way, there may be some other mental or physical issues in our life. Always there will be some entropy. Entropy, in fact, is not only the thermodynamic phenomena, but you can see it is a natural phenomena. Entropy exists in all type of situation. Everywhere entropy will be present. Entropy is also in the computational system, in your programming, data structure, everywhere entropy will be present. Like if you have collected some data, this data you are feeling that it is 100% correct, but the person who has taken the data, he or she might have done some small error and that will create the entropy. So like this, the entropy is existing in every walk of life. Everywhere some chaos is there, some randomness is there, some unwanted elements are always present, and those unwanted elements will generate the entropy. In today's lecture, I am going to discuss about few numerical problems related to the entropy and how we are going to solve these problems. I am going to discuss in my next slides. So here we have the three problems. Numerical problem number 1 is entropy change during an isothermal process. Numerical problem number 2 entropy generation during heat transfer process. Numerical number 3 is entropy change of a substance in a tank. So these 3 problems I am going to discuss and hope this will be very interesting for all of us. So the first problem about entropy change during an isothermal process. So isothermal means when the temperature remains constant, when you move from state 1 to state 2, there will not be any change of temperature. That type of processes are called the isothermal processes. So here we can see here that a piston cylinder device contain a liquid vapor mixture of water at 300 Kelvin. During a constant pressure process, 750 kilojoule of heat is transferred to the water. As a result, part of the liquid in the cylinder vaporizes. Determine the entropy change of the water during this process. So this we have to see that what are the things are given in this. Temperature is 300 degrees centigrade and this is the constant. During a constant pressure process, 750 kilojoule of heat is transferred to the water. So from here, 750 kilojoule of heat is given to this water. This water is inside this piston and the cylinder. Due to this, a part of the liquid in the cylinder vaporizes. So if you give the heat, out of this water, some part will be changed to the vapor. So we have to find out how much entropy change during this process. This we have to find out. So now we have to start with heat is transferred to a liquid vapor mixture of a water in a piston cylinder device at a constant pressure. Pressure is constant. The entropy change of the water is to be determined. So this you can see, it is given that temperature of the system is 300 Kelvin. It is a constant. Temperature is not changing, but we are giving some heat to this water and this water is converted to the water and vapor mixture. No irreversibility occur within the system boundaries during the process. So means it is a reversible process. There will not be any irreversibility in the system and in the system boundaries. Analysis we have to do. This is a closed system since no mass crosses the system boundary during the process. So it is a controlled mass system. Temperature of the system remains constant at 300 Kelvin. During this process, since the temperature of a pure substance remain constant. During a phase change process at constant pressure, this phase change is happening at a constant pressure. The system undergoes an internal reversible isothermal process and thus its entropy change can be determined directly from the equation. So here what happened? This water is changing to the vapor. So if it is a change of the phase, temperature and pressure will remain constant. So and also this is isothermal process. So how much the entropy change is there, that we have to find out. So we know that the change of entropy for an isothermal process, it is a Q by T of the system. So Q is given 750 kilojoule and the T is given 300 Kelvin. So change in entropy of this system is 2.5 kilojoule per Kelvin. So this is the change in entropy. Discussion: note that the entropy change of the system is positive as expected since heat transfer is to the system. So this is the positive and this indicates that heat is from outside to inside. If this is the system, the heat is supplied from here. So it is entering. So 2.5 kilojoule per Kelvin of heat is given. that much heat transfer is taking place, and this is creating the change in entropy is 2.5 kilojoule per Kelvin. So now I will go for the next problem, that is the numerical problem number 3. So in this we will see that the entropy generation during heat transfer process. So in the previous case we have seen that how this at a constant temperature how heat was transferred, and due to this transfer of heat how much change of entropy was happened. So delta S we have find out that it is a Q by Ts. So Q is given and Ts is given. We have found out that it is a plus 2.5 kilojoule per Kelvin of entropy was generated. Now we will see that how much entropy is generated during any heat transfer process. So we will see this problem. A heat source at 800 degree Kelvin loses 2000 kilojoule of heat to a sink at A 500 Kelvin and B 750 Kelvin. Determine which heat transfer process is more irreversible. So we have to see that which one is more irreversible. So how to find out more irreversible means if losses are more, then reversibility is more. Or if you find out the entropy and the entropy is more, means it is more reversible. Anyway, you can find out the thing. So here we will see the solution of this problem. So the entropy change for each reservoir can be determined from the equation. Since each reservoir undergoes an internally reversible isothermal process A for the heat transfer process to a sink at 500 degree Kelvin. So this you can see here that the source is same for both, that is 800 Kelvin and 800 Kelvin. Heat is here 200 kilojoule and 200 kilojoule. You are supplying. QH is here. QH for both it is same. Sink A is 500 Kelvin and sink B is 750 Kelvin. So we have to find out which one has got more irreversibility. So how we have to see it? So here we have to find out the delta S source is equal to Q source by T source. So here Q source is here minus 200 kilojoule by 800 minus 2.5 kilojoule per Kelvin, and the heat, that is entropy of the sink, change in entropy of the sink is Q sink divided by T sink. Q sink is given to 2000 kilojoule. It is coming and 500 Kelvin. So you will get 4.0 kilojoule per Kelvin. So here it is a negative and here is a positive. So we can see that here that delta S means generation of the entropy is equal to delta S total. So delta S source plus delta S sink. Source is minus 2.5 plus 4. Here you will get 1.5 kilojoule per Kelvin. So here for the first case you are getting for this 500, you are getting the entropy generation is 1.5 kilojoule per Kelvin. Now we will see for the, therefore 1.5 kilojoule per Kelvin of entropy is generated during this process. Noting that both reservoirs have undergone internally reversible process, the entire entropy generation took place in the partition. Now we have to go for the next, that is repeating the calculation in part A for a sink temperature of 750 Kelvin. So same way we will get delta S source is equal to same, but delta sink you will get plus 2.7 kilojoule per Kelvin. So now if you see the entropy generation, delta S total is equal to minus 2.5 plus 2.7. So you will get 0.2 kilojoule per Kelvin. So you can see that the total entropy change for the process in part B is smaller, and therefore it is a less irreversible. So the 700 case, where the temperature is 750 Kelvin, that case is better, more efficient than the 500 degrees centigrade, which was the case A. This is expected since the process in B involves a smaller temperature difference and thus a smaller irreversibility. So as much you have the smaller temperature difference between source and the sink, if you see here, this is 800, this is the 500 degree centigrade, and this is the 750 Kelvin. Okay, all are the Kelvin. So we can see that 2000 kilojoule per. So you can see this one, the B case, and this is the A case. So this B case, you have the less. In this case, you have the less entropy. Entropy is less than this 500. So the machine which is operating at a 800 Kelvin as a source and 750 Kelvin as a sink will perform better, as its reversibility is better, or it is less irreversible. So the case B is better, that we have observed by this discussion. Now I will go for the numerical problem number 3, that is entropy change of a substance in a tank. So this is my third problem for this lecture, and we will see here how this problem will go ahead. So a rigid tank contains 5 kg of refrigerant 134A initially at 20 degrees centigrade and 140 kilopascal. The refrigerant is now cooled while being stirred until its pressure drops to 100 kilopascal. Determine the entropy change of the refrigerant during this process. So here we have a tank with a capacity of 5 kg. Its initial temperature at 20 degrees centigrade and the pressure is 150 kilopascal. The refrigerant is now cooled and its pressure dropped from 140 to 100 kilopascal. Determine the entropy change of the refrigerant during this process. So here the pressure is dropping. So how much temperature is this entropy change is taking place, that we have to discuss. So we can see here that the volume of the tank is a constant, and thus V2 is equal to V1. So a tank, it has the constant volume. Properties of the refrigerant at both states are here. This you can see here, that this is the tank. The mass is equal to 5 kilojoule, 5 kg. Refrigerant is 134A. T1 is equal to 20 degrees centigrade. P1 is equal to 150 kilopascal. We have to find out the delta S, and heat is rejected from here, and heat and work we are supplying here. So how much is happening? So here the state is given here 1. Here it is the constant pressure, and it is as heat is rejected, this is falling down, and as it is going in the saturation line, it reaches to the liquid and vapor zone 0.2. Okay, so here from here S1 and this is the S2. So we have to find out how much S1 minus S2 is there. So here properties of the refrigerant at both states are: state 1, T1 is equal to 150 kilopascal and T1 is equal to 20 degrees centigrade. State 2 is equal to P2 is equal to 100 kilopascal and V2 is equal to V1, because here volume is constant. So from here, from steam table, at pressure P1 and temperature T1, from there you can get S1 is equal to 1.0624 kilojoule per kg Kelvin and V1 is equal to 0.651654 meter cube per kg. Now we have to see that V1 is constant. So at P2 and V1 is given here, we can find out the Vf is equal to here. This is the Vg, this is the Vg and this is the Vf. Okay. So from Vf to Vg. So we got Vf is equal to, in this condition, 0.007259 meter cube per kg and Vg is equal to 0.19254 meter cube per kg. So we need to determine quality X2. So what is here X2? Means it is a mixture of vapor and the liquid. So what is the X2? X2 means this is the X2 from here. So how much is the vapor in this system, that we have to see. So we can find out this X2 is equal to V2 minus Vf. So this V2 here is a V2 and this is a Vf. This is a Vf. So V2 minus Vf divided by Vfg. So what is the Vfg? Vfg is equal to Vf minus Vg minus Vf. So here you can get, this is the Vg 0.19254 minus this. So this all V2 is given. This we can find out from here, from the table. So you will get X2 is equal to 0.859. So it is 85.9% of vapor is present in this state 2. That is the meaning of this X2. So this X2 means the vapor and mixture of vapor and the water, liquid, 85.9% of vapor present, and only, if you see here, the 14.1% liquid water is there. That is the indication of this percentage. Okay, so now we can see here that the H2, the entropy at the 2 is equal to entropy at the SF plus X2 SFG. So this X2 we have got here, if you see here, we got here S1, V1, Vf, Vg. We can find out these all things from the table, steam table. Okay, so this SF we can get from given pressure and the volume. We will get SF is equal to 0.07188 plus X2 is 0.859 into XFG. XFG means Xg minus XF. So you will get this value. So you will get this 0.8278 kilojoule per kg Kelvin. This is the our condition for the this entropy. We got the entropy at the 2 is 0.8278 kilojoule per kg. Then the entropy change of the refrigerant during this process. So this we have to see that delta S is equal to M S2 minus S1. M is equal to 5 kg. S2 is equal to 0.8278 minus 1.0625. So we will get here delta S is equal to minus 1.173 kilojoule per Kelvin. The negative sign indicates that the entropy of the system is decreasing during this process. This is not a violation of the second law. However, since it is the entropy generation that cannot be negative. Okay, so this entropy generation minus, it is not violating the second law, but the generation should be always positive. So here we can see here that the negative sign indicates that the entropy of the system is decreasing during this process. This is not a violation of the second law. However, since it is entropy generation, Sgen, that cannot be negative. So this entropy generation is not possible. It should be always positive. So in the next topic, we will be seeing the topic 1, entropy change for an ideal gas. Numerical 2, we will see that isentropic compression of air in a car engine. Numerical 3, isentropic compression of an ideal gas. This I am going to discuss in my next lecture. Please be tuned on that. These are the references which I have mostly referring. Eunice Senegal, Thermodynamics and Engineering Approach, Tata McGraw-Hill's. I am also referring some NPTEL lectures of Dr. D.K. Mishra from IIT Kanpur. Any questions you can ask to my given mail. I also request you to like and subscribe this channel if you find that this is good. Also, if you find that there is some mistakes or there is some problems, you can write in this mail or you can give me the comment on the comment box. Thank you very much for the joining.
Like, share and subscribe. Hit the bell icon for more updates.